You've done this problem before. So let's assume I have a mass attached to a very light string. And the mass is value m, and the string length is L. And I tie it here so it can swing freely. Okay? How fast is the mass going when the system passes its lowest spot? This is a first semester problem. And in all skate, you have 60 seconds and I will call on one of you to tell me how to get the answer. Conservation of energy will get you the answer, sure. But I want you to try it again. And I want you to treat this as a point mass. Point mass has a moment of inertia of mr squared. And I don't want you to use translational kinetic energy. The system has a fixed pivot point. Use 1/2 I omega squared. Give me the angular speed of the system. Shouldn't be hard. Try it out. But again, you'll need to treat this like a point mass. So, moment of inertia. All right, should be done by now. So Hrishi, what do you got for omega?
I messed up, but I think it's square root of 2g over L.
Square root of 2g over L. Anybody concur? Too many people don't know. That's too bad. This would be 1/2 mL squared. I put L in for R times omega squared. And this is still mgl. It's not much different. So yeah, when you work this out, you'll find that omega is equal to the square root of 2g over L. Now, I actually don't want omega. I want to know how fast this is going. I want v. But you should be able to determine v because you have omega. They're connected together, aren't they? V equals omega times r. So can you prove that it's still square root of 2gl? Do so, please. Prove it's still the square root of 2gl. Stop. I'm so tired of all the sneezing and the coughing and the dripping and the blowing of noses. I'm just done. Could you guys just all be done? You get sick and just stop. Stop passing it around like it's a hot potato and somebody's still holding it all the time. Look, this is not the problem for today. This is just a quick exercise in stuff we've already done. Do you know how to do this? Do you know how to prove it? Do you take the L, square it, put it inside the radical, and show that one of the L's cancels, giving you the answer that we had. Also demonstrating that you can treat this like a rotational system, or you can treat this like a rotational system. Linear or rotational system. And since clearly Libby wants to show us how smart she is, let's take it to the actual lesson for today. If I take an object like this, a rod of mass m and length L, and I release it so that from perfectly horizontal, how fast will it be traveling when it makes it to the perfectly vertical position? So it starts horizontal, I release it, and it swings down to vertical. And more importantly, I'd like to know how fast the very bottom is traveling. I want V. I've just shown you how to do this. Show me that you can do this, please. If you're attempting to figure out how much potential energy there is, this isn't a point mass. The point mass descended a distance L, but the mass is spread out over the whole thing. What should you base your potential energy on? We talked about it a while ago, but I think you have forgotten. We call it center of mass, but we also have another name for it. Do you remember the other name for it? Center of gravity. It's an older phrase, but the center of gravity is important in this case, just like I said it would be back when I introduced the concept of center of mass. Center of mass represents the point where gravity acts on your object. We can treat the whole thing as a point mass based on where the center of mass moves to, sometimes called the center of gravity. So when it comes to how much gravitational potential energy there is, it's not based on the length of the whole rod, but where the center of mass of the rod is. If we assume it's a uniform rod, how far does the uniform rod's center of mass change? mgl over 2. So the amount of gravitational potential energy would be mgl over 2. That's how much energy the system has. Make those changes, please. This is a rod rotated about its end. What are you going to use for the moment of inertia? What's that? 1/12 is about its middle. 1/3 would be about its end. There we go. So, although 1/2 I omega squared represents the amount of energy at the bottom, you will have to use an I of 1/3 ml squared. All right, that gets you started. All right, try that. Give me at least omega, but if you can go all the way with it, get me V. I'll give you another 30 seconds, and I want to see your work. It does appear as though we've come to a conclusion. Now, some of you didn't. So I'll say that you had to do 1/2, 1/3 ml squared times omega squared equals mgl over 2. And you're solving that for omega. That was your starting place. When you get that omega equals the square root of 3g over L. Now, I asked for the speed of the bottom of the rod, but please be aware that you could ask for any place on the rod. Don't they all have a different, unique speed? So if there were objects on the rod, like a little bug here and a little bug here, the bug at the bottom would have a different linear speed than the bug in the middle, but they'd have the same angular speed. Sixth period had a hard time with that. But if we want the speed of the bottom, then we would have to say, all right, V equals omega times L, because L is the bottom. Now, if you were asked for the velocity of the center of mass, you'd put in L over 2. Because if you were asked for the velocity of the bottom, is it a little surprising to you that the bottom of the meter stick is traveling faster than a mass at the bottom of a string? Isn't that a little weird? It had half the amount of energy, yet the bottom of the meter stick is going faster. So even with less energy, the meter stick was that much easier to turn than having all the mass at the bottom. And that's clearly why it must be going faster at the bottom. But remember, do you think the center of mass is going faster? You could try, but it's probably not. The center of mass is probably going slower. Just keep these in mind, because these are the kinds of things I'm expecting you to do. I would say this is kind of level 1 kind of stuff, right? Just straightforward application of conservation of energy. Let me see if I can trick you. my first question, I will be actively trying. My second question, I will not. If we make it to the third question, I'll be back to actively trying again. All right, so a ring and a disc, both of the same mass, both rolling on the level portion of the round with a linear speed of v naught. Again, I have a ring and a disc, both mass m, radius r. And again, both rolling with the same linear speed v naught. There's a ramp, and the ramp is unique in that it's a frictionless ramp. Which one of these two things makes it higher up on the ramp? Yep.
Ring,
Why?
because it's going to be harder to like slow down.
How many say the ring will be harder to slow down, therefore it makes it higher up on the ramp? All right. That's about half of you who voted. How many of you think it's going to be the disc that's going to be higher up on the ramp? That's none of you. How many of you don't know? No, it's reasonable. I mean, I want you to come up with a decision, be able to justify it. I said actively trying to trick you, right? Because the answer is neither of them. There's no friction on the ramp. And if there's no friction on the ramp, is there anything to cause the rotational speed to change? No. So from the standpoint of this problem, they have the same kinetic energy because their translational kinetic energy is all that factors in. That's the only thing that's going to be reduced to zero. They'll still be rotating when they reach their highest point. That part will not have changed at all. The rotational kinetic energy will not change at all. So that was the easy one. That's an easy one to trick you on. And you will be tricked when it comes up on the exam. And they do that kind of stuff all the time. So let's do the real problem. Let's say that, and this is how it'll sound on the exam, something about there is adequate friction for both objects to rotate without slipping as they move up the ramp. Right? They're going to make it long, but they're not trying to make it long just to add words. They want to be specific and clear to leave no ambiguity. Does that make sense? That's why these are getting wordier. They're not getting wordier just to see if they can increase the word count of the test, although that is what's happening. They're trying to make sure you can't misconstrue the problem. So now there is adequate friction, some kind of mu, that will ensure that they continue to roll until they reach the highest point. Which one goes higher, the ring or the disc? What's that?
Ring,
What's your explanation?
like the one I said before, it's going to be harder to slow down.
I think that's a reasonable explanation. Now you guys have enough background to prove it. So I want you to start by telling me how much kinetic energy does the ring have? However, only M and V naught can be in your answer. What is the total kinetic energy of the ring in terms of M and V naught? We did this on Friday. Or I'm sorry, we did this on Thursday. We're just doing it in reverse. Try it, please. All right, so here we go. For those of you who can't do it, it has two forms of energy, 1/2 m v naught squared, and it has 1/2 I omega squared. But you can't have this in terms of I or omega. You have to put it in the terms that I said, which is m and v naught. So I'm going to have to do some substitution. I can leave the 1/2 m v naught squared for the translational kinetic energy, but I now need to put in moment of inertia. What's the moment of inertia of a ring? Good. Glad we got some of these memorized. I also can't have it in terms of omega, but it is rolling. And because it is rolling, I know that V equals omega times R. So that will be V naught over R quantity squared. The r's cancel out, and I get 1/2 mv naught squared plus 1/2 mv naught squared, or mv naught squared. That's the ring, total energy in the system. You got 60 seconds to figure out the total energy for the disk in terms of m and v naught. Got to hurry because there's only 3 minutes left before the bell rings. So hustle. Don't worry, it'll change in a second. I have a second hand. Let's go. So can I assume that if you're not writing, you have the answer? Okay, I'll count on you. "30 seconds is almost up. Go ahead. It is 3/4 mv squared. Because it's 1/2 mv naught squared plus 1/2 times 1/2 mr squared times v naught over r gives you 3/4 mv naught squared for the disk. Is it clear which one has more energy? Clear? Just throw that anywhere. We don't need it. It's just a phone. So which one goes higher up? Clear that it's a ring, right? It's going to convert all that energy into gravitational potential energy, mgh. So you can clearly find which one goes higher. So let's see. I said I was going to try and trick you again. Disk, ring. Both are on the incline now, and they're making their way upwards. They haven't been stopped yet. What is the direction of the frictional force on the disk? Up the ramp or down the ramp? Should know the answer. Go ahead.
Down the ramp.
How many of you say down the ramp? Too bad, it's up the ramp. The frictional force is the force that is causing the system to change its rotational speed. So it's the thing that causes a torque, right? So it has to be in the direction that it can cause the rotational speed to get smaller. Also, and I know you don't think of it like this, but two forces contribute to the ring or disk going up the ramp. There has to be a portion of the force upwards. So one of those things that's causing it to go up is the normal force. But the other thing causing it to go up is the frictional force. It's the two forces together that push it upwards. This is why it can go further up the ramp than just a block sliding without friction. It has that additional way of getting the energy from rotational to gravitational. And it's this. Which one's experiencing more friction? The ring or the disk? Which one goes higher? So the force pushing it upwards needs to be bigger. So yeah, the ring. I mean, that's a logical explanation. All right, that's all we got for today.